Welcome to a new video about electric circuits. This is our example number 4 where we discuss the mesh current method again, but then in a more complicated circuit. I have requested to do this video to get more insight in this mesh current method, having a very complex circuit, and this is the one of them. So we will see how we can tackle this circuit using this mesh current method. Of course, we will work out everything in our calculations step by step and also verify these in SPICE simulations. So let's look at our circuit. We have this circuit given. You see here the resistors and two DC sources. We have one DC current source IP of 5 amps, one DC voltage source of 14 volts, and we have 5 resistors, and the values are shown here. We like to calculate using the mesh current method the currents I2, which is actually shown here, the I3, which is shown here, and the I5, which is shown here. So we need 3 currents here. So how do we work this out? We have seen that in the previous 3 videos about the mesh current method, that we need to create loops in our circuit. So we will do that also here. Before we move on, I would like to designate also some nodes here, and you will see later why this is necessary. I made the node A here and node B, so this will be a potential difference later. So the solutions, first step, we choose the loop directions. In this case, we make here 3 loops because we have here a loop, another loop here, and another loop here, so we have 3 loops. So this is the IX loop, this is IY, and there is also IZ. Now, we will now write down the loop equation for each loop. That means for X, for Y, and for Z. So for loop X, what we do is we start at some point. You can also start here, it doesn't matter, you make a full circle. So I start at the ground, and I see first the minus Vs, so that's actually what I see the first. And then that will be then R1 times the Ix minus Iy, because Iy is in the opposite direction of Ix. That's actually shown here in the parentheses. And then the reason for this A and B here as the potential, because that is the potential between this node and that node. Remember, the voltage, the equation here are in volts, so we have actually voltage plus another volt, so you need to have a potential difference here. So that's the problem with this actually current source here, so we need to create a voltage source or voltage potential, the potential difference here. Now the next loop is the Y loop. You will now look at the orientation given by this arrow, and that means R1 times Iy minus Ix, because this is now defined as our positive orientation, so this is now fighting back the Ix for this R1. You also see R2 times Iy, that's the only current actually here for this mesh, for R2. And now we have R3 here also, but now the Iz is fighting back, and that's actually what you see here as minus. Okay, again, everything is summed up to 0. This is, by the way, the official expression by Kirchhoff's voltage law. The final one, Iz. Now we see now here that we start, for example, here it doesn't matter where you actually start, but if we start again from the ground, then this, it will be then not plus VAB, but minus VAB, because now the potential is now looking right this way. Then we have the R3 times the Iz minus Iy, so actually the reverse what we had before, and then R5 times Iz, and then again equal to 0. Now, we have now our 3 equations in a symbolic form. Now we need to substitute the values for this circuit. We have the minus 14 and the resistor value, so you substitute everything, and again you see the VAB is unknown here. Now the next one is then this, R1, R2, and R3 now are substituted in this equation, and the next one we have R3 and R5 substituted. And what you see here is that you have 3 equations, but 4 unknowns: Ix, Iy, Iz, and also VAB. So this is not enough to solve this problem, so we need another equation, a unique equation, that means the 4th equation, to solve the problem. So we can also write the following. That is also what we see from the circuit, that the IP here is actually Ix, because that's in the same direction, but then Iz is in the opposite direction. That is what you have here. But we know what the value of IP is, which is 5. So we can say 5 is equal to Ix minus Iz, or Ix is equal to 5 plus Iz. And now we have another equation. So if we now number the equations, first one here, the second one, and the third one, and now the final one is the fourth one, you can see that we have now 4 equations, 4 unknowns. And now we can solve this. Of course, you can set up now a matrix with 4 unknowns, but you can also simplify the problem by substituting one of these equations in another, and that's actually what I will do. So if I now substitute this equation, number 4, in equation number 1, in equation number 2, because I see there ix's. There is no ix here in equation number 3, so I will not do that there. So what we have is then minus 14 times 10, parenthesis open, ix, which is then 5 plus iz, and then minus iy, and then plus vab is equal to 0. That's this. We can now work out this equation, because you can do 10 times 5 will be 50, and 10 times iz, 10 times minus iy, this is what you have. And we now also collect the values here. You get the minus 14 plus 15, which is actually 36. That can be placed the other side, it will be then minus 36. And I also place this in order from starting VAB, IY, IZ. That is actually the order I will use for other equations also. And that will be then minus 36. Okay, this is now another equation. So let's call this equation number 5. Now, looking at the other one, which is now substituting in this equation for ix, which is actually here. Now, since there's a minus sign here, I make minus 5 here, minus iz. And again, now you can now work out the parentheses here. You can see actually 10 times iy, 20 times iy, and 60 times iy. So that's actually together, we have the 90. And you can also see that you have minus 50. But you can also do it a different way. You can say, let's divide everything by 10. That's what I have here. So I divide everything by 10. I get now just iy minus i5 minus iz. And then 2 times iy, and then plus 6 times this. Now we can again see how much iy, iz, and the other parameters we have. For example, in this case, we have only constants. So we see here the iy here. There's also 6 times iy here from this, and also 2 times. So we have 9 times iy. And we have here minus iz, but there's also 6 times minus iz here. It will be then minus 7 iz, and this minus 5 here will be then placed to the right side. So we get actually this. Okay, so you can check this for yourself carefully if this is indeed correct. So we have now our equation number 6, and now we have here three unknowns still. And there's also 2 unknowns there, but the other equation we had here, this number 3, has also three unknowns. So we have now when we collect the equation number 3, the 5 and the 6 we have here, we have now these equations in order. You see that starting from the VAB, actually for this one, and work out here the parentheses, you get here 60 times minus iy, that's what you see here, and also 60 times iz, but there's also 100 times iz will be then 160, and it will be equal to 0. So that's the first equation in the right order, voltage, VAB, IY, and IZ. Now, equation number 5 is just a copy, and equation number 6 is also here. Now, we can now set this in an equation in matrix form. So we can say, putting the 3, 5, and 6, equation numbers 3, 5, and 6 in matrix form, we get this. You see here the coefficients of minus 1, minus 60, and 160 here in the first row, and there is a 0 here after this vertical line, which is then after the equation sign. There's a first here with the 1 here, and there's a minus 10 and also plus 10, and it will be then minus 36 again after the equation sign. And we have here 9 here, but there's a 0 here, actually 0 times VAB, that's why you have 0, 9, and a minus 7, that will be then 5, because this is minus 7. We can solve this now in a way that is called Gaussian elimination. So we have now the following, that we need to eliminate the, let's say the coefficients here. You need to make this 0 and also this 0 in order to have a triangle in this form, so that you can calculate the I with Z, IY, and IX. So what you then can do is you can say, I call the rows by a small letter r, not to confuse with the resistor. So we can do R2 plus R1. That means only the change is R2 here, so R1 and R3 are the same. That means the following, this is 1 plus minus 1 will be 0, minus 10 plus minus 60 will be minus 70, 10 plus 160 will be 170, and the minus 36 plus 0 will be minus 36. And the third row is exact same, just a copy, and also the first row. Now we need to also make this 0. Now this is not a nice number compared to that one. So what we can do is, which is in this case I think the only possible way, that we multiply the second row by 9 and the third row by 70. So that's the next step. So times 9 and times 70. So, and then first row is again unchanged. You see here the results, and now you see also why we do that, because now you get the value here which is opposite of that one. Again, if we now add them up, we'll get the 0 here, which is actually what we wanted. So that's the next step, R3 plus R2. So that means the row 3 plus row 2, that means row 3 will change and row 1 and row 2 not. They will be unchanged, so you can see this, you can just copy them first and then make a 0 here and then add them up here, minus 490 plus 1530, and also for the 350 plus minus 324. That's now the result. Now we are almost done, because now you see in the final row, the third row, that you can calculate IZ, because this is one from the last row. You can see 1040 times IZ is equal to 26. That means IZ is equal to 26 over this 1040, which is then 0.025 or 25 milliamps. Now, once we have this IZ, we can calculate now IY and also IX for this circuit. Now let's collect them here, and this is the IZ we just calculated. Now we can go from the second row, and it's set minus 630 times IY plus 1530 IZ will be then equal to this minus 324. But we know what IZ is just calculated, so the only unknown is here IY. When you express now the IY in terms of the others in this form, so you actually replace this to the right side and then divide by minus 630, you get now this 0.575 amps or 575 milliamps. Now we have the IY also. Now what we now do is we look at the required currents, that is I2, I3 and I5. So do I need the IX? That's actually the question here, because the I2 is here, that only has IY. I3 is here, that has only IY and IZ, and the I5 is here, there's only IZ here. That means I don't need actually IX, so there is no need, there is no reason for calculating IX in this case. So the required currents, again, I2 is equal to just IY, so you can just take this, take this value, which is then 575 milliamps. Next one, I3, you can see the I3 here is equal to IZ minus IY. That's actually shown here. Now we know what IZ is, we know what IY is, just calculated, so we can say then this will be then minus 550 milliamps. Okay, I5 is just IZ, that is just 25 milliamps. So we have now the required currents for this example. There's actually an alternative way to solve this problem, which is actually faster in this case, but I did this purposely. We're using this matrix method, so that you can also see how we can do that using a matrix equation. So alternative solution method is the following. Bring up all these three equations we had before. Now what you can do, that is a method that you add up equation number 3 and 5 together. Why? Because then you lose these two, the VABs. So what you get is the following. You place them here on top of each other and then add them up. Just simple addition. What you get is that the VAB is now disappearing. This will be then minus 70 times IY. That will be then is equal to minus 36, and that will be then equation number 7 here. Now next step is looking at the other equation, which is also in terms of IY and IZ. That means equation number 6 and 7 now are actually two equations and two unknowns. So we have now a collection of the equation number 6 and 7. That's actually this one and that one. So this is a perfectly simple set of equations that you can solve without actually matrices. So you can say, let's multiply the first row by some number and the second row also by number, and you get now the convenient coefficients here to add them up or subtract that from each other. If I now do that by multiplying the first equation by 70 and this one by 9, actually similar multiplication will be that in the matrices, you get now this. Now you can now add them up to lose actually IY here, now 0 times IY, and this much IZ we have here, actually exact same expression as we had from the matrix, Gaussian elimination. Now you see the IZ is 26 over 1040 is equal to 25 milliamps. So exactly same result now. From there on, you can do the exact same procedure to calculate IY and then also conclude this. So from this moment, you can do the exact same procedure we had here. This is just an alternative method. So this is the circuit in the SPICE simulator. You see here the voltage source, the current source, and also the 5 resistor values. You see the current arrows where we measure the current in the branches. You see I2 is 575 milliamps as calculated, I3 is minus 550 milliamps as calculated, and also 25 milliamps as calculated. So we can say this is indeed as calculated. So we have verified this using this simulation. If you have any questions, comments about this example, please let me know. I will try to answer them as soon as possible. See you next time in another video. Take care.